Alright guys, welcome to Unit 2B. We're doing systems of equations. This is just going to be where we're solving two equations at once in the same variables. I did have a wonderful intro from Jekyll Island on the beach, but the footage got lost, so now you just got me and Isaac. Let's get into some math. First lesson of Unit 2B is going to be graphing systems of equations. The learning target is that we can solve a system of equations by graphing. Before we get into graphing systems of equations, we have to actually talk about what a system of linear equations is. So a system of linear equations is a collection of two or more linear equations involving the same set of variables. So it says or more, and it is true sometimes you'll see systems that have a bunch of equations, but most of the time we're just going to be dealing with two equations and two variables. A solution of a system of linear equations is any ordered pair that satisfies all the equations in a system. This is often referred to as the point of intersection. So it's just the place where two lines cross. So you can kind of see right there, although this is not linear because it's not a straight line, but still you can see that the solution here is going to be the points where they intersect. It is possible to get an equation with no solution, just like it is with a normal equation or a non-system, just a single equation. No solution means that there is no ordered pair that satisfies all the equations in the system. In the case of linear equations, these lines are going to be parallel, so they're never intersecting, they're running side by side. A system of an equation has infinitely many solutions when you have two linear equations in the system that have the same graph or they coincide. So basically, if you graph an equation and then you graph another equation and the line falls right on top of it, then every ordered pair you plug in that is a solution to one of the graphs will also, or one of the equations, will also be a solution to the other equation. All right, so here's an example of what it looks like if there's one solution. The lines intersect each other, they have different slopes, so there's one solution. If I look at two equations and they have the same slope but different y-intercepts, so they're crossing that y-axis at a different place, then the lines are parallel, so there are no solutions to this particular system. If you have two equations that have the same slope and the same y-intercept, then when you graph them, they are in fact the same line. So because the lines are the same, we say that there are infinitely many solutions. All right, let's jump right into some examples. Really, this is just a matter of graphing equations. So if I see something like this, first thing I notice is that they do have the same slope, but different y-intercepts. So I expect them to run parallel to each other, but does not need to be that big. But just to be safe, I'm going to graph it so you can see what it looks like. My daughter's been playing with the smartboard. All right, so I'm going to intersect at +2 for this first equation, and then a slope of 3 means I rise 3 and run 1. So 1, 2, 3, and run 1. So when I draw myself a line there, which I can do, there it is. When I draw this line, it's going to be a line like this, and it goes forever and ever in both directions. Okay, when I do the second equation, this time I'm intersecting at -2, and my slope is again 3. So I'm going to rise 1, 2, 3, and run 1. Rise 3 and run 1. So what I end up with is a line that runs just below the first line. So they're never ever going to cross each other because they're always going to be, this one's always going to be just about 4 steps ahead of the other one. All right, so my solution there would be, I would say that there is no solution, as predicted, because they were parallel with different y-intercepts. Over here, I've got the same the same y-intercepts and the same slope. So according to the chart over here, I expect it to be infinitely many, but we're going to graph it just to be sure. So my intersection is at 3, and then I have a slope of -3 over 4. So that means I'm going to go down 3 and then to the right 4. Right? So that gets me a line that looks something like this. Oops. Let me try that again. All right, that gets me a line that looks something like this. When I do my second equation, I'm going to do the exact same thing. So let's pick a different color, and I'm going to go start at 3, and then -3/4 means I'm going down 3 and then to the right 4. And I end up with a line that is going to run in the exact same spot, which means there are infinitely many solutions. That little sideways 8 means infinitely many. You could also write out the word infinitely many. That's fine as well. All right, let's get into a slightly more complicated example. We're going to start by taking this intersection of -6 and making a point right here. Then I have a slope of +2, so that's rise 2, run 1. I'm going to go from this -6 up 2 and to the right 1, up 2 and to the right 1, up 2 and to the right 1. Right? And now I'm going to do a line from this point on up. Right? Then we're going to graph that second line. This time it's rearranged slightly differently, but just remember that your constant is going to be your y-intercept. Your coefficient on your x is your slope. So my y-intercept this time is +3. My slope, there's a minus in front of that x, so that's going to be a slope of -1 over 1. So that's going to be going down 1 and to the right 1, down 1 and to the right 1. When I do my line this time, you are going to see a point of intersection. So let me pull green. When we do this line, there we go. All right, when we do this line, you're going to see a nice, pretty point of intersection right here. So what that means is that my solution to this equation is this point where the two lines intersect. And the reason for this is because remember that every point along this red line represents a possible ordered pair that I could plug in to this x and this y and have the two sides of the equation be equal. Every point along this line represents an ordered pair, an x value paired with a y value, that I could plug in for x and y and have this equation be true. So this point of intersection represents the one and only point that will be a solution to both of these equations, and that is the point over 3 and up none, so 3, 0. If you wanted to check yourself, remember that this is my x value and this is my y value, so I could substitute that in and I would get 2 times 3 minus 6 equals 0. I put that 3 in place of x, I put the 0 in place of y. 2 times 3 is 6, and 6 minus 6 is 0. So it worked on my first equation. If I want to check that second equation, then I'm going to say 3 minus, again my x value is 3 and my y value is 0, and 3 minus 3 is equal to 0. So it worked for both of my equations, which means I know that it's true. All right, last example I'm going to do for you is this one, x equals 2 and y equals -6. This is actually a really simple example, but we know that you guys sometimes have trouble remembering how to graph these equations. So remember, what I know here is that x equals 2. So I'm going to go over on my x-axis right here to 2, and I'm going to draw a line that represents every single possible point on the coordinate plane where x is 2. And that is this vertical line right here. Okay, because really if I know that x equals 2, I'm starting here, my only option is to draw a line that's on the x-axis, which doesn't make any sense, or to draw this vertical line, which makes perfect sense because all the ordered pairs along this line are going to have an x value of 2. So remember, let's write that down, that and x equals a number is going to be a horizontal line. The second one, y equals -6, let's get ourselves another line tool here. I'm going to go on my y-axis down to -6, which is right here on the y-axis, because all I know about this is that y is -6. And I'm going to draw myself a line. Again, my only two options for going through this are going to be the y-axis, which doesn't make sense, or to do a horizontal line where all my y values are -6. So the point of intersection this time is the point where these two lines intersect, just like it was over here. So that means that my ordered pair that represents the solution is the point 2, -6, which makes perfect sense because x has to be 2, y has to be -6. So there's my ordered pair. All right, guys, good luck with the examples. Let us know if you have any questions, and make sure you write questions down in the margin. There is also an application sheet for this lesson, so make sure you get that once you've finished your practice. You watching it?
Yeah. Watching it.